I've added an extra symbol, which is a micro. So Poisson micro statistics in high energy astrophysics. What does this mean? It means that in high energy astrophysics, we've been enthusiastic, if occasionally misguided, users of statistics for many decades. So a whole lot of experience has built up and ways of doing things. And the objective of this talk is to, it's different to the stuff that you've seen, there's no problems, it's just some thinking probably required. So what I'd quite like to happen is for you to say, why did you do it like that? That's not a very sensible thing to do. So I will be saying this myself once or twice during the talk, because the traditional way in which high energy astronomers do some things doesn't make much sense. And I think we need to improve our methods. So please shout out when you find something that's particularly ridiculous or difficult to understand. I used to have a job as the calibration scientist on XMM for the high resolution instrument there. So quite a lot of this stuff comes as a fruit of that experience and trying to get the instrument understood as well as possible. Calibration is obviously a vital part of doing statistics at all. So you will see some tables and some figures that came out when I was a calibration scientist. But I've had an interest in statistics for a bit longer than that, when you might see that. So what are we going to do today? The talk is about Poisson statistics. Poisson statistics is counting statistics, and it is what underlies the process of detection of individual events. We all do this. Most modern instruments now count photons. Sometimes there are lots of them, sometimes there are few, and all the methods that we use fundamentally are Poisson statistical processes, counting events. Traditionally speaking, and we've heard quite a lot about it this week, people like Gaussian statistics for historical reasons, for cultural reasons, and sometimes for no reason at all. It's just that that's the way it's always been done. But it's simply the case that you have to make a choice whether you do things one way or another, and the choice you make has consequences. And so if you choose to use Gaussian statistics rather than Poisson statistics, there will be, some things will happen, some things will be different. And it's simply a question of telling you what the effect of that decision is. You have to make a decision. The decision sometimes is made for you by default. You press the fit button and all sorts of things happen. You mustn't do that. You must be in control of the analysis that you do in high energy astrophysics and everywhere else. You must make explicit decisions and be aware of the consequences of those decisions. And I will spend quite a lot of time comparing some simple results that you get using Poisson statistics and Gaussian statistics and demonstrating that there are differences. You have to be aware of those differences, and if you're prepared to accept the incorrect answers provided by Gaussian statistics for counting experiments, that's fine. You can do that, but you should be aware that they're wrong. So my claim is that the whole of high energy astrophysics for the last 30 years is wrong because they've used the wrong statistics. And I can quantify how wrong by a few percent. But these are not religious arguments, they are objective scientific arguments, so I will put the various alternatives to you, and then you can make your choice. And people make all sorts of choices for all sorts of reasons, but if you have the evidence, if that's not a loaded word, then you'll be able to see what goes on. in each case. So there's a list of topics here. Calibration is a vital thing to get right, because what you want to do is to make a model of your data. That model has got to be as good as possible, and you absolutely rely on calibration information provided by observatories to be able to make a successful model of your data. And if that information is not good enough, you have to complain. You have to say, I need more than you've given me. So calibration is vital. We'll see how that comes in. And so one of the things that high-energy astronomers do, and nobody else in the universe seems to do, is to rebin data. And so there's a simple question: what are the reasons for rebinning data? Should I do it or should I not do it? I say it's a complete waste of time. Other people have different opinions. With any luck, we'll be able to come to some collective view of whether it makes sense or not. So this is a procedure that high-energy astrophysics often do. Complete waste of time. Goodness of fit is an important criterion as well. We haven't heard too much about it. We've heard some Bayesian equivalents. By exploring the likelihood surface, I can locate some models which are better than others. But I want to ask the question in some absolute terms, is this model any good? And goodness of fit is the phrase which is used to answer the question, when I've got a model, it may be the best of many bad alternatives, but or it might be a good alternative. So you need to know how good a model is. And then I will give some examples of point source analysis, some spectra. Background is an important thing. And when you have lots of different analyses that you've done, can you add them together? In all of this, data provided by archives is an important component as well. So again, it's up to the community to say to data providers in archives, are the data available in this archive of sufficient quality that I can do my statistics? Users should be the people that drive archive requirements, not internal agency people, not anybody else. This is generally science and statistics should place some requirements on how data are delivered and the calibration data that come with them. This is a regular expression for those of you who like regular expressions. It says macro and micro. What that means is that when we're doing statistical analyses, we're interested in both the overall global statistical properties and the individual properties of little bits of the data. So the micro statistics and the macro statistics are both important. If you want to understand physics or if you want to understand the universe, you have to do both these things. So I've got a global likelihood, and it's made up of a product of lots of individual likelihoods. Some of those individual likelihoods may be no good, and you have to be able to identify the bits that don't work, as well as the fact that the whole likelihood is good. There may be bits that are no good, and so you have to be interested. I suggest you have to be interested in both the macro statistics and the micro statistics, and I'll be showing a few micro statistical things. So I've underlined mission requirements at the bottom. So this is a job. So as well as you saying whether the methods that are available in standard tools in particular, the micro and macro methods are good enough for you to do your job. That's an important thing for you to say. So high-energy astronomers use something called XSpec for analysing our X-ray spectra. And it seems to me that XSpec could do with a good kick to get it to do some things that it doesn't do now. And so if you use XSpec or any other tools that don't allow you to make a proper exploration of the micro statistics or the macro statistics, it's up to you to write a list of requirements saying what you want those tools to do. So I would like you to think about macro and micro statistical requirements of the publicly available tools. And at the bottom I've written and underlined it, mission requirements. We specify in some rather vague way what missions should do. Flux to 5%, wavelengths to 1 angstrom, whatever it might be. There's no statistical component to this. In none of the mission requirements documents I've seen has there ever been any statistical statements. So the goodness of fit seems to me something that should be in the list of things that an instrument should do. It should give you a fit that's good at some statistical level instead of just 5%. So I think we need to make more specific demands, more specific statistical demands of instruments, and I would like you to write down how you think such a requirement could be formulated in a statistical way rather than some just vague 5% in the flux scale. That's not good enough.
Does that mean you specify your model in the instrument's proposal?
Well, you can tell me at the end. Yeah, I don't know. I of course have thought about it at least since last night, but I simply suggest that there's some improvements that could be made that would help observers understand how instruments work. So here's a little lemma, something for you. So the thing about high energy astronomers, you can form a personal relationship more or less with every photon. And that means you have to understand them all. So make every photon count. Every photon has got some physical information and you want to get it. And you've also got an instrument which gives you these things. This photon was produced in some far-off part of the universe. It travelled and went in your instrument, and it's a little nugget of information about physics, and you want to get that physics out of it. And to do this, you have to understand the photon and understand the detector. So you have to make every photon count. If there's one photon that doesn't fit your model is wrong. So and you simply have to get a better model. And similarly, if there are some bins in some parts of your detector that are misbehaving, you've got to understand your detector better. So you've got to do these two things. You've got to understand every photon and every part of your detector. And this is what the model that you make and then compare with some statistics. So how do we get at physics? We get at physics by having some lovely data, and then we think, we make a model. And in high energy astrophysics, can you see that? The data collection of photons, some events in some bins, and the events in, whoops, let's try that again. The events, so I might as well leave this one here. These are integers, events are integers, and the integers start at 0, so an observation of no events is a perfectly good observation. And the models that you make to try and understand this collection of integers, these are continuously distributed. These are real numbers. And I get at physics simply by comparing this with that, fiddling around with my models for the continuously distributed mu, trying to work out some physics. So it is important to emphasize that these are integers and these are real numbers. And so those things are always, photons events are always in detector coordinates, and this stuff here is always in physical parameters. So I'm trying to get at these by looking at what's happened in my detector. Data don't have errors. There are no errors on data. There may be errors in your interpretation of those data, but if I've got the bin and it's got 10 photons in it, those, and from a measurement that I've made, it'll never be anything different but 10. You plot an error bar on a point. That error bar is about your interpretation of those 10 photons, not anything else. It's about your model. So the only thing that have errors on are models, not data. It's convenient to plot an error bar on a data point, but you have to be careful about what it means. Data have no errors, subject to fluctuations. You must love your data, because the data are the thing that tells you about physics. And you try your hardest writing proposals, getting constantly disappointed by stupid time allocation committees. But in the end, you get some data, and you've got to love those data and understand, get to know them. You've got to understand everything about them. And you understand everything about them by fiddling with models. So those data then go in an archive, so everybody can try and understand them as well. Whereas your physical models, your physical creativity will eventually turn up in a journal with any luck if the stupid referee doesn't try and cause trouble. So you write these. This stuff will be written down, and for your colleagues in the rest of the world to look at and think about. And the way that the simple process by which information, everything else is exchanged between models on the one side, constantly changing, data on the other side, never changing at all, is through statistics. And that's what we've been talking about this week. So, data and models. So, just to make it absolutely clear, I've got a collection of integers here in detector coordinates. Never going to change. And this is where my imagination comes in. I'm making some models. So remember, this is a real number, these are integers, and this depends on whatever you care to put in there. So position on the sky, temperature, luminosity, absorption, and anything that's in physics can go over there. That's what you're trying to find out. And it's the statistical comparison of those mu's in bins with those n's that allows you to work out what the universe is doing. So, blah blah, so here are some blah blah, but we've had plenty of blah blah this week, so I'm going to give you some more. Measurements in high-energy astrophysics collect individual events. Many different things could have happened to give those events. Alternatives are governed by the laws of probability. Direct inversion, you can't just turn it upside down and find out what the physics was, because lots of things could have done the same job. So, when you work things out, you have a certain amount of knowledge, but it's important to say how well defined that is. So statistical inference quantifies uncertainties. Here are some sort of basic questions. What do we know? How well do we know it? And in particular, this is all about making decisions. So I want to do some statistical analysis which makes sure that I don't make a fool of myself when I decide to do a new observation. So how can we avoid making mistakes, and in general, what should we do next? So these are the questions that statistics tries to sort out for you. So there's just one slide like this. So there's the things used to be done in a different way in the past. Things are done in a sort of different way now. I have a certain geographical bias, because the Reverend Bayes comes from a family from Sheffield in the north of England, and Sheffield is my town. But I'm not a frequentist or a Bayesian. I'm more a Marxist as far as statistics is concerned, which means a Groucho Marxist rather than a Karl Marxist. I'm not going to join any club that would have me as a member. So this is the philosophical bit. Doesn't really matter. I'm interested in these procedures being as useful as possible. If someone cares to label them Bayesian, that's fine. If somebody cares to label them frequentist, that's fine. I'm a utilitarian. I want to wring every little bit of information out of the data that I've got, and I'm prepared to listen to anyone who can help me do this. Blah blah. And this thing at the bottom, I stress again, archives play an absolutely vital role in doing this, because if they don't provide you the data in the right way, then they're failing. And you must tell agencies that. So, getting down to some brass tacks, there's a comparison to be made between what happens when you use Poisson statistics and what happens when you use the good old Gaussian statistics, so popular with everybody. Poisson statistics gives you a statistic which is called the C statistic. I don't know if it's been mentioned yet, I haven't heard it yet. So the C statistic is the Poisson equivalent, we'll come to its formula in a moment, is the Poisson equivalent to the chi-squared statistic. And so we'll talk about the comparison between these two things over the next few minutes. So I've been a long-term adherent, convert, acolyte of the C statistic, and I think you should use it too when you have the opportunity. But, so, the C statistic is something that's based on the Poisson distribution. So here is the basic mathematical formalism that's underlying detection of events, and most of you are probably familiar with this. But it's a lovely formula. So it says the probability of detecting n events given an expectation value of mu, so this is an integer, this is a real number, is this simple formula here. Exponential of minus mu to the n over n factorial. This says everything you need to know about high-energy astrophysics. Just a question now of applying it. So it's got some properties. It's a probability, so it sums, not integrates, sums, because this is discrete, it sums to 1. And the log of this probability is this n log mu minus mu. This is the cost function for the Poisson distribution. And so n log mu minus mu is the thing you use instead of y minus y expected over sigma squared. So you'll see this on many occasions, you may have used it. It's a beautiful thing. So here are some properties of so it says up here, the Poisson probability distribution for data n greater or equal to 0. 0 is good. For a model which is a real number which is greater than 0. So mu's got to be greater than 0. Can't be 0, it's got to be greater than 0. So here are some of the first terms of this probability distribution. So this says the probability of observing nothing when you expect mu is e to the minus mu. So it immediately encompasses nothing at all. So this is very useful. So probability of observing one event is this times mu over 1, 2 events when you expect mu, and all the way up to, so there's the recurrence formula, which taught me something that I hadn't quite realised before. If mu equals n, the probability of observing mu minus 1 is the same as the probability of observing mu. Isn't that exciting? So these two are exactly the same, by definition. Good stuff, mathematics. So here is the Gaussian that we're all familiar with, so I won't go through this much. Not that I don't care for it, because it's a wonderful formula, and it's useful in lots of circumstances. But if you want to apply it to your photon counting experiments, you have to know what the consequences are. So no point in going through this again, but you can read some stuff at the top. Oh, right, but the sigma is a useful sort of number that we can all use. It tells you something about your confidence of how close you are to something. So I'm perfectly happy to use 1 sigma, 2 sigma, 3 sigma. I'm happy to know that something is a 3 sigma result or a 5 sigma result, and this shows me something about the probability involved in those numbers. So 1 sigma happens much of the time, 2 sigma, 1 in 20 odd, 3 sigma, 1 in 400 odd, 4 sigma, 1 in 15,000, and so 5 sigma, perhaps you believe that. And so again, explicitly, I'm trying to get at physics by comparing models with data via some statistics, and I do this by working out the likelihood. So the likelihood is the probability of getting the data given the model. Remember, this vertical thing means given. So what's the probability of the data I've got in all these bins, I from 1 to n, given a model? And so you have these two possibilities. If you wanted to choose between Poisson statistics and Gaussian statistics, the Poisson formula comes out like this. The log likelihood is the sum of n log mu minus mu, with a constant term that you don't have to worry about. This is the log likelihood. So maximum likelihood equals minimum chi-squared. Maximum likelihood equals the minimum C statistic. So you take minus twice the log and get this thing called the C statistic, invented by Webster Cash in 1979. This reference here at the bottom. Cash's paper tells you more or less everything you need to know about Poisson statistics and how to use it. So it took a year to be accepted, it took another year to be published, but it's a fantastic paper, and I recommend you reading it just because it's incredibly clever and useful. Now this is the Gaussian approximation to Poisson statistics, because it's still the same process, same physical process, but instead of using the Poisson formula, I'm now considering using Gaussian statistics to describe this process. I have some vague reservations because I know that the Gaussian distribution is continuous. It's not, so it doesn't have integral values, but I'm happy to ignore that by taking a point in the middle, or perhaps I should take it a little bit further. But anyway, so the fact that this is continuously distributed and this is not, means I can still use this and write down what the likelihood is. We've seen this formula before, and it's got this sigma on the bottom. Sigma is incredibly important. This is the uncertainty. So you get this automatically with Poisson statistics. There's no sigma there. So because it's a Poisson process, you know what the variance is. Sigma squared equals mu. So the Poisson process, you don't have to specify sigma. If you choose to go Gaussian, you have to make a decision of what sigma you're going to use. And this is, remember, for photon counting experiments. And there's a whole literature about how you work out this sigma. And of course, it has to depend on things that you know. And the only things that you know are these two quantities, the data I've got and the model. And so there are some simple ways of doing this. So some people say sigma squared equals n. This is the standard default alternative that you get if you run expec and don't think. Sigma squared equals n. Sigma squared equals the number of events that I've detected in a bin. Okay. As an alternative, sigma squared equals mu. So one's called data weights, and the other's called model weights, and they give you different answers. So you have to make a choice of which one to go for. And there's a whole literature out there printed that's an utter waste of time of people of proposing different sorts of formulae to make the Gaussian distribution behave like the Poisson distribution for all values of mu and n. Churazov, Gerels. Utter waste of paper. And simply because what they're trying to do is to make the Gaussian distribution behave as closely as possible to the Poisson distribution. Why not use the Poisson distribution? So the fact that it's there for you to use, you don't need to waste your time working out sigmas, but fine. You look in all the statistics textbook, it says, yes, this is a good approximation, this is a good approximation, but I'm here to tell you what the consequences of those approximations are, and mostly they're not worth it. You may have detected a certain bias in my approach. So it's your obligation as creative astrophysicists to make models. Right, so it's your obligation to make models and then compare your models to the data. So what does it say here? Detected data are governed by the laws of physics. The numerical model should reproduce as completely as possible every process that gives rise to the events in the detector. You've got to be clever, you've got to be creative, you've got to make a model that's as complete as possible. And here are some of the things that you might have to do. So the photon is made out there somewhere in some microscopic physical process, and it comes through the intergalactic medium, the interstellar medium. Things could happen to it, it could disappear, and then it arrives in your instrument. And you have to describe your instrument properly. This is all to do with calibration, but there are some subtle things as well as the overall calibration stuff. It's sometimes the case that the integrity of even an event is difficult to decide on. So most high-energy instruments actually reconstruct events from lots of different pieces that fall in different parts. So an event is made up of lots of little bits. So you sometimes. The best events are not. The best events are just single things. But there's a lot of work that goes on in actually giving you an event from lots of bits that fall in different parts of the detector, usually, of course, close to one another. And this is so event reconstruction is absolutely vital, and you should know about it. And pile-up is where two events land in one integration time in the same bin, and you can't distinguish two photons from one photon. And there are some subtle things which are a combination of these two things. So you have to be aware how good your instrument is at avoiding pile-up and event reconstruction are always there. Some instruments are much better than others. So, for example, the XMM EPIC PM has extremely short integration times, and therefore you can reliably observe much brighter sources than you can with the X-ray instruments aboard Chandra, for example, which all have integration times of 3 seconds. So pile-up is a much worse problem on the Chandra X-ray instruments than it is on the specially designed bright modes for XMM. So choose your instrument. So XMM is really, really good for bright sources. And this is not the case for some other things. So the pile-up, and I won't mention them again, but you have to know about these things. And so building up the model of the data that are in my detector, it's vital that I have a complete model which also includes the background components, which can come from a variety of different sources. And all these things, and anything else that you've identified that's relevant, go into your model, which you then compare with your data. And again, if you do your statistics properly, it's absolutely vital that you build up the model bit by bit and don't do anything like background subtraction. Background subtraction is an extremely bad idea as it destroys your statistics. So never subtract anything from your data. Your data are sacrosanct. Leave them alone and simply make a more sophisticated model, a cleverer model. And it's got to have some background components in. So one of the calibration things that observatories are not terribly good at is providing background models. Demand better background. In fact, there are no background models, but you need a background model to make a successful model of your data. So it's an important component, and observatories should be providing much better information about how to model backgrounds. They don't do it. So stamp your feet. So probably the single most important thing is instrument calibration. So this was the instrument that I helped to calibrate, XMM Newton RGS. Here are some X-ray mirrors, here is a grating, here are the RGS detectors. It's complicated, here's a grating, lots of numbers. These are the sorts of things that you've got to know to be able to make a successful instrument model. And the instrument model is an absolutely vital part of your physical model of your data. You rely on the observatories to tell you this. This is just to show you, here's long list of stuff simply to emphasize that this is a complicated business. So calibration is not easy, it's difficult to get better accuracy, better in some absolute sense than, say, 5%. And so you have to be aware of this. If your 5% is there's be some systematic error in your comparison of physics and a physical model and data, it could come from the instrument. It's not going to change, probably, but you have to be aware of the power of the comparison that you're making. It has an important component from the instrument calibration. So here is lots of things put together. So I'm doing my best to make the best the best possible model of what I've detected, and it's depending on all sorts of things, sources, backgrounds, all sorts. So this is the thing I'm really interested in. I'm trying to get physics of the universe. Calibration scientists try and get physics of the detector, so these two things somehow go together. But as astronomers, we're really interested in the set of source parameters. A whole bunch of other things go in, background in there as well. So in the end, you can calculate by comparing your model with your data, you will get a likelihood which is a function of the source parameters, some background parameters, and some instrument parameters. So mostly you will be interested in the source parameters given the stuff that the observatories have supplied, background information and instrument information, and usually forget about all this, and you just study the log likelihood as a function of the physical parameters of the source that you're interested in, or the thing that you're looking at. So I've written down here just a short list of the things that observatories have to give you for you to be able to make a proper comparison between models and data. And I'd like to emphasize that this, generally, now is as good a time as any, the only proper place where this comparison can be made is in data space. That's the data are the purest thing you've got. You don't want to mess about with them. So your model should make a prediction, or try to reproduce, I should rather say, try to reproduce what happened in detector coordinates. This is the proper place to make the comparison. This is the proper place to do your statistics. Oops. And so the sorts of things that you need to know are point spread functions, PSF, line spread functions, LSF, the overall instrument sensitivity. You need to know what background there is in there. You also need to know the stability. So they give you some numbers. Do those numbers change over the course of the mission? So you absolutely need to know this, because quite often you're interested in the variability of something. When I looked at it a while ago, is it the same as it is now? So you need to know the stability of the instrument as well. So I've written these down as calibration obligations. This is something that observatories must do for you to be able to make a successful model of your data. It's an obligation. So now let's get down to some nitty-gritty. So, perhaps again provocatively, I've titled this "Bias in Data Analysis." So what a high-energy astrophysicist does is to using XSpec or other tools that are well known in the high-energy community in general, is to make a choice between three sorts of statistics. Two of them are chi-squared statistics, one there and one there. These are Gaussian, different flavors of Gaussian statistics. So and here is the formula that has sigma squared equals n. So this is called chi-squared with data weights, because n are your data. Here's chi-squared with model weights. There's a mu here, so the model goes on the bottom, and this chi-squared will be different to that, because this is different to that. And in the middle is the good old C statistic, which has a cost function, n log mu minus mu. So I now give these three alternatives a simple problem. perhaps not the simplest problem. The simplest problem will be one bin. But you might imagine that if they had one bin with a number in, they all might agree. And they do, of course, except when you try and work out the errors, because then they'll start to disagree. But, so the zeroth order problem that I want to know what the maximum likelihood estimate of the mean counts in. I've got a bunch of observations, lots of different n's, a set of n, and I want to know what the mean n is. So all these observations are taken under identical conditions, and the number of events I detect in a bin will be different, just because that's how Poisson works. Sometimes you get something, sometimes you get another. And I now pose the question to these. If I use a likelihood calculated with chi-squared with so-called data weights, this on the bottom, and model weights, you get different answers. And here are the answers that you get. And so this is a sum of this statistic, this is a sum of that statistic, this is a sum of that statistic. This is called chi-squared with data weights, this is chi-squared with model weights. I just want one number, the mean count in a bin, and I've got lots of bins. You can differentiate this. The only thing that I don't know is mu. So I can differentiate this with respect to mu, set it equal to 0, solve it, and the answer is the maximum likelihood estimate of mu you get, 1 over mu equals the average value of 1 over n. So that's simply an analytical result that comes from differentiating this. So when I do the same job, differentiate this with respect to mu, set it equal to 0, I get this. This is simply an analytical result. So my estimate here is given by that. My estimate here is given by that. My C-statistic estimate is given by that. We know that this is the right answer because simply the average number of counts is total divided by the number of bins you've got. This is the right answer. This is the wrong answer because when you assign sigma that's n, that means the downward fluctuations have more weights than the upward fluctuations, and this pulls it down. That's why you get this expression here. This is wrong, this is wrong, this is right. Why would anyone, when they've got a problem to solve, deliberately choose a procedure which gives them the wrong answer? I don't know. So these are the biases that come out in this extremely simple procedure. If you use this, this is the answer you get. If the answer was really 100, because this is just this number over a Poisson distribution. So this is biased down by 1.5%. This is 100. This is a large number of counts. This one's right, because that's what the C-statistic does for you. And this one's biased by 5% in the other direction. And so in this simple problem, both the chi-squared statistics have failed, not by much, by 1.5% in one case and by 5% in another case. So here you are. You can use this chi-squared measure if you want. You can use that chi-squared measure if you want. But if you try it on this simple problem, you'll get the wrong answer. You may be prepared to accept that. Try it on more complicated things, you will get different sorts of wrong answer. So the bias is low. So some people. So this is a very nice book, except for one page which says it's perfectly fine to use Gaussian approximation to the Poisson distribution. In this person is wrong, or at least wrong to this extent. Wrong by 1.5% in that case, and wrong by 5% in that case. If instead of using chi-squared with model weights, you use the proper formula, which has an extra log mu there, you actually get the right answer if you use data weights. But then it requires this extra logarithmic bit. We won't worry about that. So this was a talk from a Chandra person, Vinay Kashyap, and he called it Scary Plot Number 1, about the biases that go into your data analysis if you choose to do chi-squared with model weights, chi-squared with data weights, or the good old cache C statistic, that is Poisson statistics in the middle. This shows you some simulations of a power law spectrum in an X-ray instrument. Here is the colour's not terribly good, but here is what the slope by definition is of your simulation. This is the distribution of estimates that you get out from using chi-squared with model weights. Here is the distribution of slope estimates that you get using chi-squared with data weights, and here is the distribution the distribution of values that you get for your estimates of the slope in these simulations that you get out using the C statistic. This one is more or less centered on the real answer. These are mostly too low, and these are mostly too high. So, in this simple simulation of a power law spectrum in an X-ray instrument, if you use the wrong statistical method, you get an answer which is not as good as it could be. So, if you're aware of this, if you're prepared to take that risk and compromise your physics by getting the slope of an AGN wrong by 0.01, whatever it is, fine. So that's up to you. That's what most people in high energy astrophysics do, and that's what has to stop. So this is a bit of work that I did a few years ago to compare the affected area of the RGS instrument and the EPIC PN instrument. The process was called rectification. So I'm trying to work out whether I was trying to work out whether the RGS and the EPIC PN instrument gave you the same answer when you did some statistical analysis of some AGN. So there was, I don't know, a large sample of 100 or more observations of AGN which have power law spectra. And because everybody uses chi-squared with data weights, that is 1 over n as the denominator in your chi-squared, we published this answer here, which said, here is the comparison between RGS and the PN at short wavelengths. There are two RGSs, RGS1 and RGS2, and at long wavelengths here we have RGS1 and RGS2. And the analysis was done with the spectral analysis of all these AGN, and RGS1 and the PN agreed to within 3%, minus 2.8%. It said the difference between the RGS and the PN is minus 2.8%. Difference between RGS2 and the PN was minus 2.7%. These were the published values. The agreement here, incredibly good. If the only thing you did then doing exactly the same analysis, but just do a little switch in the next spec, change my statistical method, I get a different answer. So if I was use chi-squared with model statistics, instead of minus 2.8%, I got 1.2%. The errors on these are tiny. There's lots and lots of data, so I should have put the errors in, but I didn't. So you get a different answer. You get it hit wrong by several percent. Several percent is my calibration goal is several percent, is a few percent. And just by changing the statistical method, just by changing my cost function from chi-squared to another chi-squared to something that's a bit more sensible, which is the C statistic, remember that's based on Poisson statistics, I get these different answers. What do you do? So we asked ourselves this question. We said, we better do what everybody else does. So we published this. That was because some democratic decision was taken. Democracy may not be any use in this case. I would argue this one would be a much better thing to give. At least everybody else doing their spectral analysis in a different way, they would get a different answer. So we published that, even though this one was the right. So it's simply the case that in this exercise of calibration, comparing this instrument with that instrument, the answer's different, and significantly different. The choice of statistical method makes a difference. So, the first commandment of high energy data analysis use Poisson statistics to explore parameter space. This is what the Poisson likelihood reduces to. And I like this expression so much, so simple and so beautiful, that I think it required a slide all by itself. What this says, the log likelihood is the sum over all your events, these are the things I've actually detected, of log mu, by the sum over the whole of the detector of mu. Now, I don't know what this means, but it must mean something, so please tell me. It could hardly be simpler. There's a log there, and there's not a log there. This is the sum over the data. This is the sum over the instrument. And this contains all the bins that don't have anything in. These are all the zeros. These are all the bins that have something in. The zeros are very, very important. So now we've adopted commandment number 1, and we can work out some consequences of using Poisson statistics. Here is that expression again. Log likelihood is this. I want to. Here's an imagined model where this mu is the sum of some source signals plus some background. Not necessarily point spread function or a line spread function. It's just a spread function of some sort, because bins can be anything you like. I want to know what S and B are. So I do a bit of elementary manipulation and a bit of differentiation, and I find a condition at the bottom which applies to maximum likelihood solutions of Poisson problems. The total number of counts in the best model is the same as the total number of counts in the data. If you have 10 spectra, 50 backgrounds, 100 sources, this is just a single thing. It says total number of counts in all those bits added up, data, is the same as the total number of counts in all those bits added up in the model. This is a condition which holds at every maximum likelihood solution to a comparison of a Poisson comparison of models and data. So, as you know, analytically, this condition holds. You can check whether your maximum likelihood solution obeys this condition. It should do. If it doesn't, it's the wrong answer. So this is an analytical result, a useful analytical result. May not be, in fact, it's incredibly useful. But expect doesn't tell you this. And if that condition does not hold, the chi-squared with data weights, chi-squared with model weights, it does not hold. And it sounds quite a nice condition to me. So I like that condition. Right, other Poisson properties. The nice thing about you can divide your data however you like with Poisson variables, because a sum of Poisson variables is another Poisson variable. So divide them, add them up, do what you like. The analysis that you get in a Poisson analysis is completely independent of the binning that you use. It's not true for chi-squared, because the bias changes. The Poisson process, in its most formal definition, is a constant rate, and of course sources go up and down. So there is a formal thing called the inhomogeneous Poisson process, where the rate is a function of time, and if you integrate between two limits from t1 to t2, this is also a Poisson variable. So this is called an inhomogeneous Poisson process. So there's a formal justification for using Poisson processes for variable sources as well. And so, for example, the arrival of customers at a restaurant or for a cafe, a lot come in the morning, and it gets quiet, and then quite a lot at lunchtime, and it gets quiet, and there's quite a lot in the evening. So the rate is going up and down. But the Poisson variable, that's a function of time, is a good model for this. So you use Poisson statistics to explore parameter space, to make your comparison between models and data. As well as finding a maximum likelihood solution or any other solution nearby, or any other solution, I want to make the judgment of whether this model is any good. So I've located a model, but I still haven't said whether this model is a good model or not in some absolute sense. So goodness of fit is a separate issue, it says here. So again, I'm comparing these three possibilities. Chi-squared with data weights, this, I call this S. The C statistics, C is this is cost functions, and the good old the chi-squared with model weights, I've called it Q here. And so what I'm interested in is the goodness of fit properties of these statistics, because although these two things are properly considered to be separate issues, I can ask the question, tell me your goodness of the power of this statistic as a goodness of fit criterion. And this is possibly the most important plot in the whole talk, which shows you, because we know that underlying the whole process of detection of events is a Poisson process. So I've simply calculated, as a function of a model value mu that goes from 0.1 down here up to 100 here, the Poisson expectation values of these quantities here. This one here, so I've just put a Poisson probability in the front of this, summed it over from 0 to infinity, divided by 1. So what's the Poisson expectation value of that? S, and there it is. What's the Poisson expectation value of C? Even though I'm using this for exploring parameter space, I'm also interested in knowing whether it has any goodness of fit properties. These are two different things, remember? And what's the goodness of fit? What's the Poisson expectation value of this quantity? And here you see the answers. So the Poisson expectation value of these numbers here as a function of mu. This is the default that you get. It's supposed to be a goodness of fit statistic in XSpec, and it does that. So it reaches a maximum somewhere of a few counts, which is much, much greater than 1. I really like a goodness of fit statistic that is 1 under circumstances. The C statistic, which many people have rejected because you see it a million times in the literature, it does not have goodness of fit properties. It does. It has better goodness of fit properties than the default standard that you get. The goodness of fit properties of C are much better than S. This is the default you get. It's rubbish. Whereas, as a goodness of fit statistic, this quantity here, n minus mu squared over mu, is identically equal to 1 for a Poisson distribution, independent of mu. This is an analytical result. The Poisson expectation value, nothing to do with chi-squared. The Poisson expectation value of this quantity is identically equal to 1, making it a very useful goodness of fit statistic. So, combination of these two things, the two commandments of IAG data analysis, use Poisson statistics to explore parameter space, and 2, to judge whether this is any good or not, calculate Pearson statistic, that's what Pearson did, n squared minus mu over mu. That's the Poisson expectation value of that is 1, so that tells you, gives you a suggestion of whether the model is any good. So this tells you how to get to the model, and this tells you whether it's any use or not. So I see time's getting on. So the maximum likelihood estimate is something I think that you should be interested in, but not all you're interested in. You have to explore the likelihood surveys, especially in the region of the maximum likelihood, because this tells you how well you know the different parameters that you're trying to. So I've written down here a list of the sorts of things that I think that you need to think about. The likelihood is the key statistical concept. Both frequentists and Bayesians. Bayesians go and do something with it, that's fine. Frequentists don't do much with it, that's fine. I got into likelihood by reading a book called Likelihood, published in the 70s by someone called Edwards, who said, I'm just going to use the likelihood. I'm not going to bother about the fights between the Bayesians and the frequentists. I'm just going to use the likelihood. sort of happy to use the likelihood as well. But sometimes there are good reasons for fiddling with it. So get the maximum likelihood solution, to compute the goodness of fit statistic, and then you have to work out some uncertainties following. Always calculate 1 sigma, blah blah. So you've got to do some, when you get there, you've got to do some work. You've got to explore the surface near there, and you've got to not just look at the likelihood surface. You've got to look at the implications for the data in the model. So you pay attention to everything that's going on. So we heard some. So I'm interested in the changes of this in the vicinity of the maximum likelihood estimate or anywhere else. So I need to know how to interpret changes in this log likelihood, and these sort of equivalent here. But it comes down to changes of the order of unity. Not very interesting. You can't really tell the difference. We had yesterday. I applaud that. Changes of 1 or 2 or 3, maybe something going on. Not worth paying too much attention. As this number gets bigger, then something might be happening. Yeah, 10, maybe something. If it gets to 100, you're up to something. There's something you have to do. So differences in the log likelihood of this means something, and you've got to do something about it. So even though you've got a goodness of fit, this is perversely enough the Pearson statistic that I call Q. P is reserved for something else. It's a probability. So Q is next to P, and so Q. This is the Pearson statistic. It's rarely one, and there can be many reasons for this, but systematic errors are one of them, and we don't really know how to deal with this. But there are some people giving it a good go, so we should pay attention to these people. And so how do I interpret the goodness of fit statistic? This is really bad. This is the sort of thing that you want. This is also bad. If you get Pearson statistics of 0, it means that you've done something wrong. And so one is a... Right, so let's get down to some practical... finally, after all this time, let's get down to some practical examples. Can you see this? Because I can't see it. Not terribly well. Well, believe it or not, this is a Chandra image of Zeta Orionis, one of the Orion belt stars. So it's an X-ray image, and can we turn some lights off? Would it be better? Because, right. So here I've got some data. This is data space. I'm always going to make the comparison in data space. I'm interested in making a model of these data and work out some, working out some physics about what's going on in good old Zeta Orionis. And although you can't see it, and so here are the data, and this is from DS9, and you'll see at the top here that this is right in the middle. The maximum count's about 90 or something here, but 90 and a few 10s here, and if we ever get the lights down, this is all black. There is nothing in many of those pixels. So I've got, typically when I'm doing some point source analysis, I'm trying to make a model of this stuff. That's getting better. Yeah. Oh, you can see that there's another one here. So there are 2 sources here. Can you see that this fake thing here? So this is Zeta Orionis itself. This is another O star nearby. Its companion. I'm trying to make a model of all the pixels here. So most of them got nothing in. And there's a few counts here and a few counts and lots of counts there. So how do I make a model of this? I put a PSF here, move it about, optimize the position. I put a PSF here, move it about. But because I know the identity of this star and the identity of this star, I move them together. Because the instrument will probably have some pointing errors, but it'll affect them both the same, so I move these around together, and I have some background in there. When I do this, I get some numbers out. So you make a mark on, every mark on the paper has got to mean something. So I should, so what I've done, show, this is some Chandra data, this is Chandra X-ray observatory, show CXO target, this is some code of mine, show CXO target history. This is what the Zeta Orionis binary system is called. This is Zeta Orionis A, this is Zeta Orionis B. I go off to a catalogue, get their positions, and keep the results in here. So, and I make some marks on the paper. And every mark on the paper is either some metadata that relates to the observation. So here is the instrument, here is the OBS ID, this is when the observation started. There are a whole bunch of them taken at different times. And here are the source positions that I've calculated. I've calculated by making a Poisson model of all the pixels by using a PSF and some background and 2 PSFs. So I've making my model of my Poisson mu's and comparing them with the n's that I've got. And these are the numbers that I get out from a maximum likelihood. Analysis of this, and I get some cap rates out, and I get something here which is called log L. It's slightly misleading. So this is, in fact, a detection statistic. It's the difference between the likelihood for flux equals 0 and the maximum likelihood. So this is a likelihood detection statistic. And you see it's big here and it's bigger there. And here are the count rates with some errors attached. So I've got to this maximum likelihood solution by solving the equation d likelihood by d of all the parameters equals 0. I've solved that equation. And I've worked out the errors by solving the equation likelihood minus L equals maximum minus a half. So I've solved equations for getting all these numbers. So I've iterated the position to get the best position, but then when I've got there, I've solved this with some d likelihood by d something equals 0, and calculating the errors by looking for the places where the maximum likelihood is decreased by a certain amount. So this is the error associated with that. I haven't plotted the errors associated with the position, but I could have done. Here is the observation time. These are my likelihood detection statistics, and here is so here is a Poisson analysis of a bit of an image, which allows me to work out how bright these 2 stars are. And I need to do them simultaneously, so it mixes up two PSFs. Oops, I don't need to do that. So I can do some point source inference. So, but again, I rely on somebody to tell me what the PSF is. So in the olden days, Chandra didn't tell you what the PSF was. So I made one up. I fit some functions, kink functions to lots of different things, and I come up with some numbers. But then the Chandra source catalogue came along, and it gave me, for all the sources in the Chandra source catalogue, it gave me a PSF. Associated with every entry in the Chandra source catalogue is a file which contains a picture, an image of the PSF. So I wanted to compare for another of my favourite Wolfram spells, WR134. So this is what I got when I used my default PSF. Same numbers, blah-de-blah, with a smaller detection statistic. This is the difference of log likelihoods. I get this count rate for WR134 using a default one. Then I use the custom PSF. So let's use the PSF. There's something that the Chandra source catalog has given me for this OBS ID for this particular source. The PSF is in this file here. I'm going to use that instead, and I get a different answer. And so the count rate's different by a few %, and you get a much better detection statistic. So this means that this PSF is rather better than the other one. So thanks, Chandra source catalogue, for giving me a better PSF. The point is that it's up to the Chandra people, it's up to the XMM people to give you the best possible PSF. In this case, PSF, because you need the best possible PSF to get the best possible answer about what this thing is. And here it's different by a few %. A few % might be important for your physics. You need observatories to do their job properly. So like maximum likelihood, likely around there, that's what the position, that's what the solution is. what's the quality of this, the goodness of fit of this solution? Here I make a little plot which shows all the pixels around the WR134. In the middle here I've got the data are at the top, and the model that comes from this PSF that they've given me is at the bottom. I want to make a judgment of whether this PSF is any good or not. I want to know whether this Q statistic, the Pearson statistic, has a reduced value of 1 or not. Does it? No, it doesn't. So what's going on? So in each of these pixels, data at the top and my model at the bottom made out of a PSF, and because this is a maximum likely Poisson, the total number of source counts in the source in the model is the same as the total number of counts in the data. And in the middle there's a difference of 100. So this one's not terribly good. This is one of the reasons why this is such a bad number, nowhere near 49. I'd like it reduced value close to 1 because that's how Poisson variables behave, but it's 271, a reduced chi-squared of quite a lot, 5. 5's bad. And it comes because mainly this one's useless. There's a difference of 100, so the model is giving me twice the number of observed counts. Well, quite a lot of these others look pretty good, even when there's nothing. So no 0 counts in this bin, 0.6. Don't ask me why that one's bigger than that one, but must be. There's all the various things. The information goes in there. Haven't noticed that before. That's slightly peculiar, but anyway, there you go. A couple of noughts there. There's lots of noughts down here. There's 1, blah de blah here. So this is perhaps it's in the PSF. Who knows? So most of these look quite good, but I'm perfectly happy to deal with these zeros here because Poisson does the zeros for you. And these look all quite good. So there's just a bit of trouble in the middle here. That means that this is not a perfect solution. Data on the top, model on the bottom. That one looks good. That one's not too bad. You can, in fact, that this deficit of 100 here is made up. You've got a few 10s here and blah, 30 there, and the total is about the same. But the PSF is not perfect. So you need these two things. You need to find a good solution by exploring the parameter space with your Poisson statistic, and then you need to do this to see if it's any good. And this one's not perfect. So it says here point source historical obligations. Here is an incomprehensible table from Pollock 1987, which says Wolf-Rayet stars in the Einstein Observatory. The relevant bit is this bit here. It is good old WR134 detected 30 years ago in 1979. So, and of course, an obvious question is, how do these two things compare? It's not a completely straightforward question to answer. In fact, I don't really know how to answer it properly yet. And the reason being that, so there are various things that you could do with this. Presumably, a Bayesian person would have a way of using this to construct a prior of some sort. And then I could then inform in some way my analysis that I've worked out here with just a likelihood by that prior. But I want to be slightly more flexible than that. I want to redo that analysis and give it equal weight. Prior seems to me to be something that you define once and that's it. There's no fiddling with it. And that it will be a much more sensible idea to treat these two observations 30 years apart with much more equally somehow. So what should happen is there should be an archive that I can go to do precisely that. There should be an Einstein archive which will serve me the data, which will allow me to redo this analysis, and then I'll do these two things together. There's some sort of interesting comparisons to be made here. So this is the same star observed 30 odd years ago to this Chandra one, but some of these numbers here look really nice. So here is the detection statistic that I also used in 1987. It's defined in exactly the same way as this one. So now we've got 4,611 for WR134 with this count rate. And before, in a relatively long observation, strangely enough, reported in units of 100 seconds. That's what things used to be like in the old days. You used to have instruments that were less sensitive, and you got less time on them. And now they're more sensitive, and you get much more time. Isn't it odd? Anyway, so Higby observed that for about 10,000 seconds, or 10 kiloseconds, I got this number here for the count rate. And observing only for 1,000 seconds, my likelihood detection, my log likelihood detection statistic was only 3. And this number here times that number there means that there were only 7. 9 6s are 54. A tiny number of photons. This is the same as this. And my detection of only a value of 3 and a handful of photons. I've got a perfectly reliable detection with only this number 3. It agrees with that 23 and probably agrees with that 4,600. So you can do a lot with a handful of photons if you do the right sort of analysis. You can answer other sorts of questions. So now I've got some sources. I now am interested, it says here, I'm calculating mu, before it just said mu as a function of xy. Mu, so this is the Poisson model, as well as a function of xy, it's now a function of t. Here you see zeta Puppis, O star, great big O4, and here it is in the, you probably can't see it, but here it is in the small window of the EPIC PN instrument, and I'm now interested in its variability. So I can do the same job in time bins. Guillaume will tell you tomorrow much more about what to do in the time domain, but you can answer some questions in the time domain. This shows you that zeta Puppis goes up and down by a few percent. This is a hot star people, this is a very important result. It's only a few percent. So what do you need to know from observatories to be able to interpret this? You have to know that this is not the background, so you need a background model. You need to know that it's not the instrument, so you need some information about the stability of the instrument. But independent analysis of other things shows that the EPIC PN is incredibly stable to 0.1% over many years. So this is real variability at a few percent level for this O star coming out from doing a Poisson analysis. So now we go into the spectral domain. This is where things really start to get weird. So this is exactly the same data. There's a different projection. I've got my event list, and now I'm projecting them into energy space. Pity about that. From the top this says mu as a function of energy. And for the EPIC PN small window data, exactly the same data. Instead of studying its spatial and temporal properties, I'm now looking at the energies of all these events. And this is what the EPIC PN's estimate of this spectrum looks like. And it looks like that. Lots of counts in lots of bins, and if instead of whoops, this is slightly out of date, but never mind. So good old zeta Puppis again, this big O star. There was a picture here which showed a Chandra image of this thing. So I have an image, I put some gratings on top, I get a dispersed spectrum, and I get a high resolution spectrum that looks like this. And I'm very keen to plot this in proper data space. So here I have these are real event counts. This is what zeta Puppis looks like at high resolution. And you may say, well, you were the RGS calibration scientist, why don't you show RGS data of this? The reason I showed Chandra is because the Chandra data are not as good as the XMM data, because the resolution is fantastic, but the sensitive area is much lower, so the number of counts you get in individual bins for the brightest X-ray O star in the sky is tiny numbers. So this is 5, there's 1 and lots of 1s and 0s here. So I've got to have methods spectral methods that deal with 1s and 0s. So here is a similar plot for a little part of the spectrum of the good old Zeta Orionis again, which just puts some flesh on the bones of what I just said. The RGS has many more counts than in some parts than the Chandra gratings. But you're dealing with lots of bins with zero in. You ask yourself the question: is this how is this different to an image? So the high energy community has been perfectly happy to construct Poisson models for imaging, for doing source detection, where most of the bins have got nothing in. But for some reason, the spectroscopists don't like that. And they don't like that. So what they do, they try and get rid of all those bins with zero in by adding bins together. So rebinning in spectral analysis is something that happens routinely and makes no sense. But it's what the high energy astrophysics community does. They don't like zeros, they like Gaussian statistics, and so even though they're perfectly happy to accept the results of a Poisson analysis in the spatial domain, for some reason the vast majority of X-ray spectroscopists have an utter aversion to low count rates. So in things like this, they will do some rebinning, which gets rid of all those zeros. Why would they possibly want to do that? It's an odd sort of. It's because the methods that were developed 30 years ago, 40 years ago, people still like them. They were developed for instruments which were much less sensitive, the resolution was much poorer, but they decided they wanted Gaussian statistics. There were some important papers that showed how useful chi-squared was. People are really keen to continue to use Gaussian statistics and chi-squared. This is a pseudo-religion. There are all sorts of incantations and magic spells which are said. There's even sacrifices of one sort or another. These people are mad. But it's the whole community that's mad. How do we stop this? So this is the sort of thing So to bin or not to rebin a spectrum. What are they? I really love Gaussian statistics, and if I rebin on my spectra, I'll be able to use Gaussian when I've got no zeros. And there's something called the dangers of oversampling. People say you mustn't have lots of bins. You can't oversample your LSF or your response function. But this is an utter misunderstanding of the thing we talked about the other day about it's the correlated noise, not the correlated signal, that's the important thing. So this is a fundamental misunderstanding of what sampling does. It saves time, everybody does it. Here is the incantation. It improves, you see this written in the literature all the time, improves the statistics. This is utter nonsense, but an utterly meaningless statement, but it's written down all the time. Improves the statistics. And there's group therapy in the form of group PHA. This is a well-known tool that exists, and people use it all the time, and it should be retired. And something else peculiar about normal methods, people always plot log plots. Why the hell do they do this? I don't know. So, and the sacrifice that is made is the sacrifice of information. You join lots of bins together, you're discarding information. You don't want to do that. So these are why people do it. They don't do it for any good reasons. They should stop. And the cons are you throw away information. I think 0 is a perfectly good measurement. This is the famous piece of music by John Cage, which is 3 movements of silence. So the spaces between events are just as important as the events themselves. 0 is a very important number. We must not discard it. Images are never binned, of course, blah, blah, Poisson statistics, all this stuff works. Better get moving. So these spectra alone, don't rebin, use Poisson statistics. XSpec has it for you. It's called the C statistic. It's not the default. It was going to be the default. Some nasty political shenanigans stopped this happening. So the default is still something that's wrong. Change it immediately. I won't talk about backgrounds, I won't talk about all this stuff. So here what XSpec doesn't do is to allow you to remember results of model fitting. So I wrote some code which puts these things in a file and then allows me to add data up from lots of different analyses that I've made. And this shows, again, I want to make every decision a statistical decision. And when I was calibrating or helping to calibrate the RGS, we got some new line spread functions. And here are some plots which, for the whole of the history of the life of the RGS, shows you an old PSF with 34 observations added together and a C statistic here of this. And the next one is a bit better because I've added these 34 observations. My C has gone from 140 to 120. So I have a statistical justification for the release of this new line spread function calibration file. One of the things that Expect doesn't do for you is it doesn't give you the power to inspect the details of the models and the data that you've got. So I wrote some methods that allowed you to do this. Go into the guts of Expect, get all the stuff out. If you want to do this, we should get Expect to do it. So us RGS calibrators noticed. So this is the number of events that I've got. This is a model. Here is the background, and there's a background model. So you can't get at all these numbers normally, but it was noticed that there were some zeros in these. These spectra contain several thousand bins, and some of them were zero. And in a typical spectrum, you had about a dozen of these things which were zero. And some of them, so these zeros compared with this model value here, this is perfectly all right. This one's not perfectly all right. This one's not perfectly all right. So by looking at the details of these spectra, we were able to realise that there was something wrong in the software, which worked out the effective area wrong. So pay attention to the detail, to the minutiae of your data and models, and you will be able to work out things both about your detector and about the universe. Forget about all that. So this fuzzy thinking. So data are wonderful, so you've got to take care of them, and instruments behave in different ways. So this is the calibration describes this. You've really got to investigate your data, both and your models, as much as you look at lots of different plots in both model space and data space. Forget about log-log plots, they're useful, blah-de-blah. Always report 1 sigma errors, nothing else. Make every decision a statistical decision. And we still have some primitive methods which somehow called aperture photometry. This is the olden days where aperture photometry was all you had. We now have the capacity for making complete models of all the data. And by making complete models, you will get every little bit of information that the data have about the universe, about what you're interested in. And you've really got to make the best model possible. It's your obligation. So there's something that I sort of think of as the KS test. It doesn't mean Kolmogorov-Smirnov, it means kitchen sink. There's an expression in colloquial English they took everything but the kitchen sink. Means that every. If you need the kitchen sink in your model, it's got to be there. Your model has got to be as detailed as it needs to be, and no more. But it's got to have everything in. And if this means making a complicated model, you've got to make a complicated model. So here are 10 commandments of data analysis. The most important ones being don't rebin and n equals 0 is good. So there we go. That's the end.